Welcome to our video series. We will love to hear your ideas for future videos. Now, let's dive into the topic of unpacking the tokenization bottleneck. In this page, we will cover the massive capabilities of modern artificial intelligence and the specific glitch where it fails to count basic characters like the letters in the word strawberry. We will identify the root cause as a legacy compression algorithm from 1994 acting as a gatekeeper to our smartest machines. This outdated technology creates a critical bottleneck known as byte pair encoding. Despite artificial intelligence being able to write complex code and draft legal briefs, it still struggles with basic counting errors. This occurs because the model is not seeing letters as we do. Instead, it relies on an old file compression trick that was never originally intended for deep learning. We are going to tear down this system to understand why these errors happen and how they impact performance. By the end of this discussion, you will understand the hidden layer that stands between human language and machine processing. Modern AI is staggering in its ability to explain quantum mechanics, yet it famously crashes when fed obscure usernames. This represents a basic counting error that we must address. We will look at how this 1994 compression algorithm acts as the gatekeeper to the world's smartest machines. Moving on to the core illusion of large language models, it is essential to realize that these models do not actually read words, see letters, or hear sounds in the way humans do. When you ask a model to write a poem about a strawberry, the input text goes through a tokenizer, which acts like a physical barrier or a giant vault door. This tokenizer smashes the text into fragments. On the other side of this door is the large language model matrix, which consists of a massive grid of numbers and vectors. The model does not see the word strawberry, it sees a sequence of barcodes. This is the blind spot of modern AI. The model writes rhyming poetry not by hearing the acoustic frequencies of the words, but by memorizing the mathematical proximity of tokens that usually appear at the ends of lines in its training data. This concept is what we call the rhyming phantom. The takeaway here is that the artificial intelligence reads barcodes rather than text. To truly understand the limits of any model, you must inspect the barcode scanner itself, which is the tokenizer. The model is effectively blind to the individual characters until they are processed into these mathematical units. This realization changes how we perceive the output of a language model entirely. To understand why we use this system, we must look at the scale of the dependency extreme. Designers faced a difficult choice when building these systems. On one hand, we could not use raw characters because processing them one by one is far too slow. This approach leads to a computational meltdown because the attention mechanisms in these models scale at a rate of n squared. On the other hand, we could not use whole words because that approach is too rigid and cannot handle new or misspelled words. Therefore, researchers needed a compromise that balanced efficiency and flexibility. This compromise led to the development of subword tokenization. If you look at the visualization, you can see a precarious stack of individual letters on one side and a rigid block of words on the other. The middle ground allows the model to handle a manageable number of tokens without losing the ability to construct any possible word. However, if a word is not found in the vocabulary, it might be assigned an unknown token, which appears as a red box in our diagram. This compromise is the foundation of modern language processing and is necessary to keep our systems running at a high speed while maintaining general capabilities. Let us look closer at the execution logic of byte pair encoding. Originally, this was a 1994 file compression trick. The process involves scanning the text and ruthlessly merging the most frequent adjacent characters into a single unit. It builds a fixed vocabulary based strictly on statistical co-occurrence rather than linguistic rules. As a senior developer note suggests, this is a brute force statistical proxy for language structure, not a semantic parser. In the diagram, you can see individual character blocks like N, E, and W through a greedy statistical frequency process. The algorithm sees that E and R appear together often, so it merges them into a single token. Later, it might merge these again to form the word new. This merging happens over and over until a desired vocabulary size is reached. The problem is that this process is entirely mathematical and does not care about the meaning of the words. It simply follows the path of highest frequency, which can sometimes lead to very strange ways of breaking down human language into fragments. This statistical approach is efficient, but ignores the underlying structure of the language, leading to some of the issues we will explore later in this presentation. There are different philosophies when it comes to slicing text, primarily byte pair encoding versus wordpiece. Byte pair encoding, used by models like GPT-4 and LLMA, merges purely on raw frequency. This is very fast but often creates linguistically meaningless chunks. For example, the word unbelievable might be chopped into strange pieces like Eli, and Abel. On the other hand, the wordpiece method used by models like BERT evaluates the likelihood of the combined pair versus the individual parts. This results in cleaner, more logical splits that often resemble morphemes, which are the smallest units of meaning in a language. In our illustration, you can see the top beam being jaggedly sliced by the greedy frequency merge of byte pair encoding. The bottom beam shows the maximum likelihood merge of wordpiece, which creates more uniform and recognizable blocks like believe, and able. The key takeaway is that the exact same string of text creates wildly different vector dependencies, depending on which tokenizer choice the engineers made during the design phase. These choices have deep impacts on how the model perceives the world and the relationships between different concepts in its memory. Now we come to failure point number 1, which we call Frankenstein slices. The vulnerability here is that byte pair encoding is highly optimized for common patterns. However, rare data falls outside the statistical window of the training phase. This has a significant impact on foreign names, chemical compounds, and localized variables in code. These rare strings are shredded into meaningless mathematical fragments. In the visual, you can see the word pterodactyl being chopped up into pieces like pt, odd, and ill. These pieces are then crossed out because they lose their original meaning during the process. It is important to remember that the large language model itself is not necessarily broken. Instead, it is being forced to hallucinate the concept of a dinosaur from 5 completely unrelated and messy data fragments. When the model encounters these rare fragments, it has to work much harder to reconstruct the original concept, which often leads to errors in logic or factual accuracy. This is why models often struggle with very specific technical or cultural terms that were not frequent enough in the initial training data to be represented by a single, clean token. This fragmentation is a major hurdle for precision. Failure point number 2 is what we call the arithmetic nightmare. This occurs because there is a logical gap in how numbers are represented. You cannot easily teach an artificial intelligence to learn that 380 plus 1 equals 381 if the numbers themselves do not share a consistent structural representation. Under the hood, multi-digit numbers change their physical shape based purely on how often they appeared in the byte pair encoding scraping phase. In the diagram, the number 380 is represented as a single large yellow cube. However, the number 81 might be split into 2 blue fragments, and the number 38 might be split differently into white fragments. This creates a shape mismatch crash. A senior developer note explains that this is why providing code interpreters or calculators drastically improves numerical reliability for AI. The tokenizer actively fights pure mental arithmetic by providing the model with inconsistent building blocks for different numbers. It is like trying to do math when the digit 5 is a circle and the digit 6 is a triangle. The relationships between them are hidden from the model because it never sees the digits as separate, logical entities in a sequence. Failure point number 3 involves the mysterious ghost tokens. The symptom of this issue is that prompting certain obscure strings causes models to output total gibberish, refuse the prompt entirely, or experience a mathematical panic. The root cause is that these strings were scraped from specific places like Reddit gaming threads during the initial vocabulary construction phase. They were merged into single atomic tokens like solid gold Magikarp. However, the disconnect happened because these specific tokens were later excluded from the actual model training corpus. The takeaway is that the model has a key to a room that was never furnished. It reaches for a semantic vector associated with that token and finds absolute zero. When the model encounters a token it has in its vocabulary but never learned about during training, it does not know how to handle the resulting mathematical void. This leads to unpredictable behavior where the model might start repeating words or crashing. It is a haunting reminder that the vocabulary and the training data must be perfectly aligned for the model to function correctly. These ghost tokens represent a breakdown in the pipeline between data preparation and model learning, showing how fragile the system can be. We must also consider the security vulnerability known as prompt injection via boundary splitting. In this exploit, adversaries force token splits using unusual spacing or Unicode characters. The mechanism involves safety classifiers that look for dangerous token sequences. By artificially altering the byte pair encoding boundary, a malicious payload can bypass pattern matching filters. For example, if a filter is looking for the word bomb, an attacker might split it into separate tokens like B and ohm. The safety filter sees these as harmless fragments and lets them pass through. However, once they reach the model, the semantic reconstruction process joins them back together into the original dangerous concept. As the watch out note explains, you cannot easily patch this at the filter layer. The vulnerability exists entirely in the gap between the tokenizer fragmentation and the model semantic reconstruction. This highlights a fundamental flaw in using pattern matching for security when the underlying representation of the text can be manipulated so easily by changing how words are broken down into tokens. This gap creates a space where malicious instructions can hide and then reappear once the model processes them, bypassing modern security measures. Another major issue is the systemic architecture flaw known as the token tax. This reveals a clear bias in how models are built. Byte pair encoding vocabularies were constructed primarily from English internet text. The penalty is that non-Latin alphabets and morphologically rich languages are heavily fragmented. This requires significantly more tokens to convey the exact same information. In the illustration, a simple English sentence like "Hello, my name is Sarah" might take only 7 tokens. However, the same sentence in Hindi or Korean could take 35 tokens, which is a 5 times compute penalty. A senior developer note points out that this directly translates to 4 to 5 times higher API costs, slower inference speeds, and artificially restricted context windows for global users. This creates a digital divide where users of certain languages are effectively paying a tax for the way the technology was designed. It is not just an issue of cost, it is an issue of performance and accessibility for the majority of the world population who do not use the Latin alphabet as their primary writing system. This inefficiency makes large language models harder to deploy fairly across the globe. Fortunately, there is an escape route known as the megabyte architecture. The goal of this new approach is to eliminate the tokenizer entirely and allow the model to natively read, spell, and process raw continuous bytes. Meta's megabyte architecture is a breakthrough that uses hierarchical processing. By grouping raw bytes into patches, the quadratic attention bottleneck is applied to a much shorter sequence, which effectively defeats the n-squared scaling problem. In this system, there is no fixed vocabulary, no Frankenstein slices, and no token tax. The diagram shows the old tokenizer being smashed and crossed out. Instead, a stream of raw UTF-8 bytes flows into a local model that handles individual bytes and a global model that handles large patches. This allows the model to understand the fine-grained details of every character while still maintaining the ability to see the big picture. This shift away from subword tokens could solve many of the reliability and bias issues we have discussed, making models more robust across all languages and technical domains. By dealing with the raw data directly, we can avoid the errors introduced by the middleman of tokenization and create more accurate machines. Our teardown is now complete. Let us review the architectural takeaways. First, you must evaluate before engineering. Tokenization dictates your context limits and costs, so always inspect how your target model tokenizes your specific domain data, especially code, math, and non-English text. Second, do not trust token boundaries for security. Token-level boundaries are fundamentally brittle. Pattern matching safety filters are vulnerable to boundary-splitting prompt injections, so defense in depth is required downstream of the tokenizer. Finally, prepare for the byte-level horizon. The tokenization layer is a temporary 1994 patch to a 2015 compute problem. You should watch emerging architectures like Megabyte and Mamba that will eventually deprecate subword abstraction entirely. Understanding these limitations today will help you build better and more secure applications tomorrow. We are moving toward a future where models can read text as humans do, without the messy interference of outdated compression algorithms. This brings us to the end of this video. We hope you found it informative and engaging. If you have any questions or suggestions, please leave them in the comments below. Don't forget to like, share, and subscribe for more content like this. See you in the next video.